Oh, yeah. All right. This is Friday, November 6th, 2020. This is Physics CP lecture on the concepts of impulse and momentum. All right, here we go. Zoom in a little bit. Newton's second law says the sum of all the forces acting on an object, there you go, the mass symbol sigma, meaning add together all the forces, is called the net force. And this net force is equal to the product of the mass of an object times its acceleration. So for any, and by the way, for the force of gravity, the weight of an object, that's equal to the mass of the object times its acceleration due to gravity. Nice. So really, it's like a, a subset of Newton's second law. Newton's second law says you add all the forces together. This net force is m times a. Force of gravity, the weight of an object, is m times the acceleration due to Earth's gravity. Now I'm going to take just Newton's second law, F equals ma, and remind you students that acceleration is defined as the change in velocity divided by the change in time. And I'm sorry that the iPad mini is re-auto-focusing every time my hand gets in front of it, but it doesn't take long, so there you go. Also, I think it makes more sense if I put it this way. I think you can see it a little bit better. All right. So what I'm going to do is I'm going to substitute the definition for acceleration into Newton's second law. Again, acceleration is a vector. It has magnitude and direction. And the little triangle is the Greek letter delta that means change in. So change in velocity, whether it's the magnitude and or the direction, they both count as an acceleration, divided by the change in time. Okay, well, so F equals m times change in velocity divided by change in time. Simple substitution. My next step is I'm going to multiply both sides by delta t, the change in time. And although I didn't write it so it looks like it does, this is in the numerator, that's in the denominator. They're going to cancel. And writing this one last time, it's F times delta t is equal to m times delta v. Now, what is that? This is an entirely new concept in physics for you students. This is not anything that we've had before now in this course. The term on the left is called impulse. It is the product of force times distance. And we're talking about a situation where I have some object, let's say, and I'm applying a force to that object for some amount of time. So I guess off the top of my head, I could say, all right, like I apply a force of 3 newtons for a time of 2 seconds. That would be called the impulse. The units of it are newtons times seconds. Newtons times seconds. The term on the right is called the change, because of that delta, change in momentum. A new term that you haven't had before. Change in momentum. Its units are what you get when you multiply mass, which is in kilograms, times velocity, which is meters per second. Yes, indeed. Kilograms, meters per second. This entire equation or expression is named the impulse momentum theorem. You students are at home. If you were in my classroom, we would provide you with reference sheets during your exams and quizzes, tests, assessments. So there's no need for you to memorize it, even if you were in my classroom. And at home, of course, we expect you to be taking notes and to freely refer to these notes whenever I'm assessing you. So no need to memorize it. The students do tend to refer to this for some reason as fat MAV. I don't know how they come up with that because it says F delta T equals M delta V, but students tend to call this fat MAV. I don't know why. All right, so the new concept for you is this idea of momentum. You've probably heard the word, but here in physics class, just like the word work, it has meaning that is very formal and is defined by an equation. It has a relationship. The symbol for momentum is lowercase letter p. The formula for calculating the momentum of an object is mass times velocity. Because velocity is a vector, something that has both magnitude and direction, I'm going to remind you that it's a vector by writing the little vector arrow above the velocity variable. Mass is a scalar. There's no direction to 10 kilograms, it's just 10 kilograms. Velocity has direction, like I'm going east, I'm heading to the right. When you multiply a scalar times a vector, you get a vector. So I'm going to add the little vector arrow above the lowercase letter p as a reminder to you that momentum is a vector. If you like, I can write out momentum as a sentence, and I could say momentum is mass times velocity. So that's just saying the equation, but it's saying it in words. Momentum is mass times velocity. Because velocity has a direction, momentum must have the same direction. Let's just write it this way. P and V, so momentum and velocity have the same direction. P and V, momentum and velocity have the same direction. If the velocity is heading up, the momentum is heading up. If the velocity is heading south, the momentum is heading south. Great. This is a new concept. It's different from any of the other stuff you've had before. Before I even do an example with it, I'm going to try to anticipate a misconception that revealed itself yesterday when I dealt with the other physics class. So first, a little history, background, I don't know, reminder, review. If I had a 1 kilogram mass, and if I were to accelerate it at 1 meter per second squared, and I know I'm writing it to just 1 sig fig, but this is by definition. If I had exactly 1 kilogram, infinitely precise, going at exactly 1 meter per second squared of acceleration, that would be 1 Newton of force. In other words, 1 Newton is defined as 1 kilogram meter per second squared, mass times acceleration. A Newton of force is 1 kilogram meter per second squared. The kinetic energy of an object is given by the formula 1/2 times mv squared. So its units are kilograms. The meters per second for velocity becomes squared. And so that makes it meters squared per second squared. So kinetic energy, meters squared per second squared. Oh, I guess I can add my camera from that view. Work, you might still remember, was a force of 1 Newton over a distance of 1 meter. Okay, so what does that mean? That means the units of work are called Newton meters. A Newton meter, oh boy. So work with me on this one. A Newton is a kilogram meter per second squared. So this is a kilogram meter squared per second squared, which is a joule. So a joule is energy, a joule is work. Work is a Newton meter. A Newton meter is a kilogram meter squared per second squared. And in addition to these units, now we have added to that this new one called momentum, which is mass times velocity, not mass times acceleration, not force times distance. So the units of momentum, crazy enough, well, not crazy, are kilograms meters per second. Yowzers. They all look pretty similar, but they're not the same thing. Each one has its own units, right? So I could say one variable has the units of kilograms. One variable has the units of meters. One variable has the units of meters per second. One variable has the units of meters per second squared. For that matter, one variable has the units of seconds. One variable has the units of kilogram meters per second. One variable has the units of kilograms meters per second squared. And one variable has the units of kilograms meters squared per second squared. How about that list? All right. This is where I should be calling on random students. Memory quiz. Eric, the units of kilograms are associated with which variable? You have to unmute first, child. Say that again. Meters. Oh my goodness. Dylan Machuca, do you agree with that? Does Dylan Machuca exist today? Sure, you do? Okay, so when we talk about distance, we're talking distance in kilograms. Wow, you guys, you're not doing so well. And did Jaden ever show up? I'm guessing not. Daniel Pack, save us. What variable has the units of kilograms? What is the name of the variable that we use that has units of kilograms? Daniel. Why do I not even see Daniel? Because Daniel has left. Okay. Ouch. All right, moving on. Sean. Oh, come on, guys. Seriously? I wrote this whole list of different units. Each one is associated with a different variable that we use in physics. I just wanted to start with the very first one and say, what's the name of the variable whose units are kilograms? Thank you. That's all I wanted. Well, I wanted two things. I wanted an answer and I wanted the correct answer. Two things. Answer, correct answer. You gave me both. Kilograms are the units we use for mass. This isn't mass. This is the units list I wrote down. So these are meters. Meters, wait, let me mark down that Sham is on my good list today. Okay. Meters are the units for what variable? Oh man, Augustine. Yeah, it could also be displacement. I'll, go with that one. Distance, displacement, length, those things are all in units of meters. What is the name of the variable whose units are meters per second, Joseph Q? I agree. Velocity. What is the name of the variable whose units are meters per second squared? Tenrusi. Not really. Oh, wanting to lose points today, are you? Hmm, that can be arranged. Yeah. The other thing is, okay, say something. You have to say something. And not sure is not one of the things you can say. Best guess. Meters per second squared. Can you not see where my pen is pointing? Okay, so what's the name of the variable? Look, kilograms was the units for the variable of mass, right? Meters was the units for length, for which we use x or delta x sometimes, right? Meters per second, what was that variable called? Yeah, so we would do v for velocity or speed even. And you're the next one on the list. What is meters per second squared? What's the variable that has those units? Yes, that was painful. That was very painful. Okay, next volunteer. What is the variable whose units are seconds of time? Harshit. Yes. What is the variable whose units are kilograms, meters per second? Ray. Interesting. Yes, momentum, represented by lowercase letter p. What is the variable whose units are kilograms, meters per second squared? Zara. Yes. So really, I should use F for the variable name, right? Force. What? Yeah, and really, you should have said force, not newtons. So these things are called newtons. These things are called kilogram meters per second. This has its own name. This one does not. Just like this one does not. This one does not. We don't have a name that means meters per second. We don't have a name that means meters per second squared. We don't have a name that means kilogram meters per second. We do have a name for kilogram meters per second squared, and that name is a Newton. Okay, next one. What is the name of the variable whose units are kilograms meters squared per second squared? Tyler. Can I ding you? Tyler, do you ever pay any attention to anything anyone ever says? Or are you just a teenager? Yeah, it shows. Okay, the question is, what is the answer? Finally. Yeah, it's energy. Energy or work, it's called a joule. So these two only have their own name. This one is called, whoops, this one is called a joule. This one is called a Newton. None of the others have names. Wow. Okay. So what's happening is today you get this new one, kilogram meters per second. Don't confuse it with kilogram meters per second squared or kilogram meters squared per second squared. These are three different meanings. They're not the same thing. They just are very similar. Oh man, there's your 3-minute break. Take your 3-minute break right now, kids. All right, we're back from break. I just added uh, two labels on this uh, scribbling here, where I said, look, this upper line was were the units. This lower line was the name of the variable associated with those units. The variable mass has units of kilograms. The variable of distance, x or y or r, has units of meters. The units of speed or velocity has units of meters per second. The units of acceleration are meters per second squared. The units of time is seconds. The units of momentum are kilogram meters per second. The units of force are kilograms meters per second squared, which also is known as a Newton. The units of energy are kilograms meters squared per second squared, which are also known as joules. Now, let's do an example. I have a ball. This ball has a mass of 2 kilograms, which means it's like over 4 pounds, and it's moving at 6 meters per second, which means, wow, you would not want to stand in front of it to try to catch it. Momentum, well, heck, we can put all kinds of things here, right? We know its mass is 2 kilograms. We can say that its velocity is 6 meters per second. It's going at a constant speed, so we could say its acceleration is 0 meters per second squared. We can calculate its kinetic energy by 1/2 mv squared, and that would be 1/2 times 2 times 6 squared. I get 36 joules. And now we have this new variable, momentum, which is mass times velocity. That would be 12 kilogram meters per second. That's the new one, 12 kilogram meters per second. Notice it is not the same thing as kinetic energy. I keep trying to zoom in and I'm unable to do that, which is very strange. Huh. Maybe if okay, I'm not going to worry about it. Your students can see what's going on well enough. What if I have a car? So this would be another example. And this time, believe it or not, the car is heading west. This car has a mass of 800 kilograms and it's going at, let's say it's going at 40 kilometers per hour. Kilometers per hour. Because I love torturing you students with having you to do unit conversions. If it's a kilometer per hour, that is not a meter per second. You need to convert it. Yowzers. 40 kilometers per hour converts to how many meters per second? Calculate, please, because I'm about to call on you. Matthew Baldovino, what do you get? I'm still waiting. As everyone remembers, there are 1,000 meters in a kilometer, 3,600 seconds in an hour. That's what I got as well. So we'll call it 11 meters per second west. What then is the momentum of this car? And my new volunteer for that one is Jacob. What is the momentum of this car? Ooh, Fabian, do you agree with that? Uh-oh, what would you say? So, no units? And finally, no direction? Those are different. Which one is it? Yes. Okay. So all of you guys are not rounding very well. If I multiply 11 times 800, I do get 8,800. And I'm only going to do this to 2 sig figs this time because it was just 2 here. So it actually said, if I round off first and then multiply it, I get 8,800 kilogram meters per second west. If I left it as 11.1111111111111111, or for that matter, if I do 11.1 times 800, the calculator says 8888, well, 8880 or 8888.88888889, in which case you would properly round this thing up to 900, 8,900 kilogram meters per second west. I am not going to punish you if you round off only at the end of the problem. But when you round off, please round up when you're supposed to. Don't just truncate it. So I will accept either of these two answers for this example. Okay, we made it through the first page of my notes from the other day. What if I have a ball? So here's another example. And I let this ball fall. Oh man, the mass of this ball, I guess, is 4.0 kilograms. And I'm going to release this ball from rest. And I'm going to let it fall for 3 seconds without air resistance. And my question is, at the end of those 3 seconds, what is its momentum? So this is a new example. This is a free fall situation. I have a ball. I'm dropping it from rest. It has a mass of 4 kilograms. What is its momentum after 3 seconds have gone by? Okay, I don't want you to give me the answer, but Augustine, are you done with this calculation? Okay. Siddharth, what'd you get? Standing by. Jonathan, do you agree with that? As did I. I'm going to round it off to 2 sig figs, and I'm going to call it negative 120 kilogram meters per second. Not sure that you said per second as opposed to per second squared, but it's momentum. And for those of you who were wondering, how do we get that? Well, first, this was an old one-dimensional kinematic problem where I need three givens. One of the givens was the initial velocity. One of the givens was the time. And we assume that this takes place on Earth, so the acceleration is g 9.80 meters per second squared downward. What I'm interested in is what is the final velocity in the vertical direction after 3 seconds have gone by. My shopping list is initial velocity, time, acceleration, and final velocity. The equation that connects these four variables to each other is the one that I refer to as equation 1. Final velocity in the vertical direction is equal to the initial velocity in the vertical direction minus g times t. When you plug things in, you get 3 times 9.8 is 29.4 meters per second downward in the vertical direction. Finally, a mass of 4 kilograms times a velocity of negative 29.4 meters per second is a momentum of negative 120 kilogram meters per second. Ta-da! All right, that knocks off another page. Oh man, we have so much more to go and so little time. Yikes. Let's move on quickly to page 3 because you have homework due Sunday at midnight and it's on material I haven't even covered yet. So, yikes. Collisions and explosions. Now, this sounds exciting to be teaching you about explosions, but it's very boring. We're not exploding anything. Look, I have my two hands. When I bring them together, that's a collision. When I take them apart, that's an explosion. That's it. Two or more things coming together is a collision. One thing separating into more than just one part, two or more parts, that is an explosion. And just to mess with your mind, an explosion is a collision going backwards through time. Forwards through time, backwards through time, forward through time, backwards through time. Or you can say a collision is an explosion going backwards through time. One is the other going backwards through time. And the equation doesn't care about time. So it's going to be the same equation no matter what. All right. I'm worried about time. So I'm going to give you the short version. I'm going to display for a moment the notes from yesterday, and I will try to. This page is already posted online. We don't have time to really get into this right now. What I will mention is that one of the fundamental principles in physics is that energy is conserved, meaning we can't add it to the universe, we can't remove it from the universe. From chemistry class, you guys had matter is conserved. You use that whenever you balanced chemical reactions. Einstein's famous equation, E equals mc squared, really allows us to convert matter into energy and theoretically energy into matter, but it's always conserved. So even in the nuclear consideration, energy and matter are conserved. Now, here's today's new material. Momentum is conserved. And we're talking about collisions and explosions. No matter what is going on, momentum is conserved. So here, pick it up from here. I'm not going to write it again. I'm just displaying my notes from yesterday because this part is relevant for today. I show a ball and it's going to hit a box. And when I add together all the momentum before the collision, that is going to be equal to all the momentum after the collision. There are three types of collisions. One of them is called a perfectly inelastic collision. And you don't need to see this part. In a perfectly inelastic collision, the objects stick together. And significant for us, kinetic energy is converted into other forms of energy. Think of a car crashing into a truck. Some of the car's kinetic energy is transformed into the sound energy of the crash. Some of the energy is transformed into heat energy. And a lot of energy is transformed into deforming the car, crumpling it up. Kinetic energy is not conserved when things stick together. I said there were three types of collisions. An elastic collision is one where it's just dribbling a basketball. So it bounces, it doesn't stick to the floor. It bounces, but it doesn't come back to its starting height. The third type of collision, and we're only going to be dealing with these first and last ones, I think, this year. This third collision is called a perfectly elastic collision. And that's where the objects bounce off of each other perfectly. Kinetic energy is conserved. I'm going to pause while you write it down. Tyler, let me know when you are ready. Maybe I shouldn't rely on Tyler. He seems to have a frozen screen image and isn't here anymore. Okay. Oh, now your image is unfrozen. Are you are you ready for me to move on? So basically that's a no. You know, you could just say no. Children, we're under 10 minutes left in the class. Okay, I'm moving on because we're way too short on time. I'm not even going to create new examples. Maybe I should. Yeah, sure. Okay. Collisions and explosions. I have that ball and it's going to hit that box. This ball is going at 12 meters per second and it has a mass of 7 kilograms. This box has a mass of 10 kilograms. And it is just sitting there. This is going to be perfectly inelastic. They're going to collide with each other. What happens? Well, the sum of all the momentum before they collide is equal to the sum of all the momentum after they collide. Before they collide, that's going to be 7 kilograms times 12 meters per second to the right, plus 10 kilograms times 0 meters per second. Well, that means I have 7 times 12 is 84 kilogram meters per second. This is all before they collide. After they collide, it still has to add up to a total of 84 kilogram meters per second. Which one will be moving faster after they collide? 7 or 10 kilogram mass? The ball or the box? Mason H, what do you think? Speculate. After they collide and stick together, which one do you think will be moving faster? The ball or the box? And Eric, do you agree with that? Wow, sad. So, no, children, because they stick together. And if they're stuck together, then they're both moving at the same speed. Ha! And that means this 84 kilogram meters per second that they have afterwards is equal to the 7 kilograms times the unknown final speed plus the 10 kilograms times the same unknown final speed. I can use the distributive property and say, all right, add together the two masses because they are stuck together. They're both times the same final speed. Therefore, I can say 84 kilogram meters per second is equal to 17 kilograms times the unknown final speed. And this physics problem, we're trying to find the final speed. So on my calculator, I go 84 divided by 17, beep, beep, beep. And to 2 sig figs, it says 4.9 meters per second to the right is the final velocity of these two objects that have a perfectly inelastic collision. It is not halfway between 0 and 12 meters per second because they don't have the same mass. If they happen to have exactly the same mass, then yes, the final speed would be the average of their two masses. That's true in a perfectly inelastic collision. Now you're going to have some homework tonight where I'm trying to see. Huh. Let's do another one where they stick together. By the way, on your homework, there is a problem where they bounce off each other. Do not use kinetic energy to solve that problem. Only use momentum. Okay, here's our last example. I have a ball going to the right. It has a mass of 5 kilograms. And it's moving at 4 meters per second. to the right. There's a ball moving to the left. And this one has a mass of 8 kilograms. And it's moving to the left at, oh gosh, let's say 11 meters per second. Okay. And they stick together. What is the final momentum? Well, the sum of all the momenta before they collide is equal to the sum of all the momentum after they collide and stick together. Even if they don't stick together, this statement is always, 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 always true. Oh man, here's the timer that says we've just reached the end of the period. I'm going to blast through this. Look, 5 times 4 is 20 kilogram meters per second. 8 times negative 11 is negative 88 kilogram meters per second because it's to the left. 20 plus negative 88, 88, 68. So negative 68 kilogram meters per second. Again, I get to add the masses together. So 8 plus 5 is 13 kilograms times the final velocity. Therefore, the final velocity is 68 divided by 13 is negative 5.2 meters per second. If you look at the homework, you'll see that there is a problem with the two